identify various simple and mixed acid-base disorders based on bicarbonate concentration, partial pressure of carbon dioxide and pH. First we will check out a little basics and then we will go straight to different scenarios. For identification of the acid-base disturbance, we have to follow a step-by-step approach. If you see values randomly, you will have difficulty in deducing the disturbance. So first step is, what is the pH? Normal pH of extracellular fluid ranges from 7.35 to 7.45. Clinically, when the pH decreases below 7.35, it is known as acidosis, while if it increases above 7.45, it is known as alkalosis. So, for identification of acid-base disturbance, we need to first and foremost see the value of pH. If it is less than 7.35, it's acidosis, more than 7.45, it's alkalosis. Next, we need to find out the cause of acid-base disturbance, whether it is a metabolic cause or a respiratory cause. Some fundamentals here first. In bicarbonate buffer system, bicarbonate ion combines with hydrogen ions forming carbonic acid, which then dissociates into carbon dioxide and water. Now this equation can proceed either way in different types of acidosis and alkalosis. When hydrogen ions increase, bicarbonate combines with hydrogen ions and reaction proceeds towards this side. But in the process, the concentration of bicarbonate ion decreases. So what is happening is that bicarbonate ion is preventing the change in pH, but in the process it is getting used up. On the other hand, if more carbon dioxide is produced or respiratory system is depressed, this reaction will start proceeding in opposite direction. Since reactants this side will be more, so this will produce H+ ions. So based on which side the reaction is proceeding, we define acidosis as of two types. First one, where bicarbonate is being used up or its concentration is decreasing due to addition of non-volatile acids. This is known as metabolic acidosis. While in the other one, partial pressure of carbon dioxide is increasing. This is known as respiratory acidosis. Now remember, normal value of bicarbonate is approximately 25 milliequivalents per liter, while that of partial pressure of carbon dioxide is 40 millimeters mercury. So next thing we have to see after pH is the concentration of bicarbonate and the partial pressure of carbon dioxide. In acidosis, if bicarbonate is less, we call it metabolic acidosis, and if PCO2 is more, we call it respiratory acidosis. What will happen in alkalosis? In alkalosis, if it's due to loss of hydrogen ions, hydroxyl ions of water will combine with carbonic acid and the reaction will proceed this way, forming bicarbonate and water, thus causing increase in bicarbonate concentration. This is metabolic alkalosis. While if respiratory system is hyperactive, it will excrete more carbon dioxide, causing decrease in PCO2. This is respiratory alkalosis. So if we find pH is more, so it's alkalosis, and in alkalosis, if bicarbonate concentration is more, it's metabolic alkalosis. If PCO2 is less, it's respiratory alkalosis. Now because of this equation, we can also think of how body will compensate for this acidosis. For compensation of metabolic acidosis, this PCO2 is detected by the chemoreceptors, which are also directly stimulated by hydrogen ions. So it increases the ventilation, causing decrease in PCO2. So in metabolic acidosis, bicarbonate decreases and PCO2 also decreases as a compensatory response. If the case is other way around, that is PCO2 has risen due to respiratory problems, then this will add hydrogen ions into the solution. In this case, our kidneys compensate by secreting hydrogen ions and retaining bicarbonate ions from the tubular fluid. So bicarbonate concentration rises. So basically, the change in compensated variable is in the same direction as the cause of change. If PCO2 is rising, as a compensation, bicarbonate also rises and vice versa. Similar thing you can apply in alkalosis. Okay, let's go straight to our scenarios now. So here 6 scenarios are shown to think about it and try to solve it. Okay, so first step is pH. So with pH we can say that first and fourth scenarios are acidosis, while second and third are alkalosis. Now let's focus first on the acidosis scenarios. So after seeing pH, we have to look for bicarbonate and PCO2. In acidosis, either bicarbonate is less or PCO2 is more. So let's look at the values. In first case, bicarbonate is less, but what we see here is that PCO2 is also less. So what is this? Is this respiratory alkalosis? No. Remember, we defined the disorder based on pH. So we have already identified the disorder as acidosis based on the pH. And now go in a step-by-step approach. So since bicarbonate is less, this is metabolic acidosis. And less PCO2 is because of respiratory compensation. In fourth scenario, PCO2 is more. So this is respiratory acidosis. Can you now identify the causes in second and third scenarios? Okay, see, in second and third scenario, pH is more, so obviously this is alkalosis. Now look at the values of bicarbonate and PCO2. In alkalosis, either bicarbonate will be more or PCO2 will be less. Here in second scenario, we see that PCO2 is less. So answer is respiratory alkalosis. And bicarbonate is less due to compensation. While in third scenario, bicarbonate is more. So this is metabolic alkalosis. While PCO2 is more due to, again, respiratory compensation. Now let's come to fifth and sixth scenarios. In fifth scenario, pH is normal, but values of PCO2 and bicarbonate are abnormal. Bicarbonate is less and PCO2 is also less. Then what is this? Is it that the compensation is returning the pH value to normal? For that, we should know how much is the normal compensation in pH. In metabolic causes, value of PCO2 after compensation can be calculated from this formula. PCO2 is equal to bicarbonate plus 15. And for respiratory causes, compensation is defined differently for acute and chronic respiratory causes. So in acute respiratory acidosis, bicarbonate increases 0.1 milliequivalents per liter per millimeter mercury increase in partial pressure of carbon dioxide. While in acute respiratory alkalosis, bicarbonate decreases 0.2 milliequivalents per liter per millimeter mercury decrease in PCO2. In chronic respiratory acidosis, there is increase of 0.4 milliequivalent per liter of bicarbonate. While in chronic respiratory alkalosis, there is decrease of same amount of bicarbonate per millimeter mercury decrease in PCO2. So check in our scenarios of metabolic acidosis and alkalosis. Is compensation adequate? Use the formula and check. Yeah, here it's adequate compensation. But you see, despite compensation, pH is not actually normal. The compensation tries to return it closer to normal but not to actual normal value. Let's go back to fifth scenario. In this, is the compensation adequate? If you use the formula, it appears PCO2 is much less than expected by compensation. So actually, it's a mixed case of metabolic acidosis and respiratory alkalosis. So this is a mixed acid-base disorder. Okay, let's see sixth scenario. pH indicates acidosis. So let's see values of bicarbonate and PCO2. Oops, they are going in different directions. Bicarbonate is less and PCO2 is more. So both are causing acidosis. So this is a case of mixed acid-base disturbance caused by both metabolic and respiratory acidosis. Well, take-home messages to identify acid-base disorders. First look at pH, then look at the values of PCO2 and bicarbonate to identify the metabolic or respiratory cause of the disturbance. The corresponding values of the remaining variable demonstrates compensation, the amount of which is determined by the formula. The direction of compensation is in same direction as that of the